So tonight's presenter is Dr. Joseph F. Horn. He's a professor of aerospace engineering at Penn State University and also the associate director of Penn State's VLRCOE. Works in research and instruction for areas of flight dynamics, modeling and simulation, controls, handling quality, and autonomy in rotary-wing aircraft. Dr. Horn has worked for Piasecki Aircraft Corporation as well as Sikorsky, and then he conducted his PhD research at Georgia Tech. He's an associate fellow of AIAA and also received the 2017 AIAA de Florez Award for flight simulation. He's been an editor-in-chief for the Journal of the American Helicopter Society. He's currently the Deputy Technical Director of Aeromechanics for VFS. So without further ado, I'll turn it over to Dr. Horn.
Anyway, thanks, Chris, and thanks everybody for coming. So today I'm just giving a fairly broad overview of some of the research I've done in rotorcraft flight dynamics and control here at Penn State under VLRCOE, which is the Vertical Lift Research Center of Excellence. If you're not familiar with that, it's one of the 3 research centers in the U.S. Devoted specifically to vertical lift and rotorcraft, funded by the Army, Navy, and NASA. I should mention, part of the idea of the center is to draw in other research programs. So we do a lot of research outside of that grant. And in fact, I think 3 of the 4 topics I'll talk about today is actually funded from other research grants that we brought in here. So so let's go to the next slide. So here's an outline of what I'm going to talk about. So first I'll say, rotorcraft flight dynamics control is a topic I've pretty much worked in my entire career. Maybe a few projects here and there that are not rotorcraft related. I've been doing this since 1992 when I came out of my master's degree in college, worked at Piasecki Aircraft, PhD at Georgia Tech, and then worked at Sikorsky for a time as well, and then 21 years here at Penn State. So it's a great field to be in, one of the most complicated systems to look at, I think, especially from a flight dynamics control perspective. So today I'm going to give an overview of some of our facilities here at Penn State, briefly, in terms of modeling and simulation, our flight simulator, and also our indoor flight laboratory. Then get into a very hot topic right now, which is simulation control of VTOL aircraft. And then external slung loads. I'm going to talk about some of those projects. I'm going to focus on one in particular we've been working for the last 5 years. And then another great topic in rotorcraft flight dynamics is shipboard landing. I think since I started at Penn State 21 years ago, I have had a project related to ship landing almost every year. Seems to be the research topic that keeps on giving. So, but I'm going to focus specifically on a recent project we've been doing. I think is really cool on scaled experiments, autonomous ship landing that we're doing with NAVSEA Carter Rock. And then I'm going to wrap up with control design for high-speed compound rotorcraft, another topic I've worked on for a very long time, ever since I started. When I was hired by Frank Piasecki back in 1992, was working on compound rotorcraft related projects. And today I'm going to focus on work we've been doing under the Adaptive Digital Autonomy Automated Pilotage Technology, what we normally just call ADAPT, project with Piasecki Aircraft and the U.S. Army. Next slide. So let's start with facilities. Go ahead and next. So first I'll talk about simulation is a huge tool in flight control, flight dynamics for rotorcraft. So always important aspect of the research. I'll actually start with those bottom two bullets. Army NASA GenHel is a flight simulation code that's been around for a long time, written in Fortran, developed by Sikorsky, but then published by the Army. I've gotten a lot of mileage out of that code. It really let me cut my teeth on blade element simulations. I was lucky enough to work a little bit with Jim Hallett when I was at Sikorsky, who recently passed away. He was the developer of that code. Starting to phase out use of that finally. Flight Lab is another great piece of software, very powerful. Worked with ART on a few different projects. Has tremendous capability in terms of modeling even flexible blades and all sort of variant of dynamic inflow. But we have two pieces of software we developed in-house, which I find very helpful. It's good for the students to see the internals of flight sim software, understand what's going on. One of them I call PSU HeloSim. So it's a rigid blade element model, very similar to the GenHel model. It's essentially derived from that with some modifications. Basic lookup tables for the various airfoils and aero components on the aircraft. And I've implemented it completely in MATLAB Simulink in a modular format. A lot of people are down on MATLAB Simulink these days because of the cost of the licensing, but I could say it's saved me tremendous time in terms of training students with that software. Since a lot of it is somewhat self-documenting, especially the Simulink diagrams. Another thing it gets dinged on is for execution speed, but if you have the compilers, I find it runs almost as fast. For example, if I do U860 and PSU HeloSim and autocode it runs about as fast as the old Fortran version, and with basically the exact same model. And then, of course, the nice thing is we can implement controllers in that environment very easily. So, done a lot of work with dynamic inversion, which is a very powerful control design method, as well as explicit model following, which is maybe a little bit more commonly used in the rotorcraft world. I even had a student, Mike Spires, who worked on implementing robust control methods like H infinity within a DI and EMF framework. And then the other tool I'll talk about a little bit later, we call DEPSim, which is something I worked on with Continuum Dynamics. It's a variant of that same code, but it's specifically set up for eVTOL. So implementing electric motors and individually driven rotors. And then the big factor there is we've coupled it with a Charm rotor module. I'll talk more about that in a minute. Next slide. So I've always liked doing piloted simulation with my simulation work. I think it draws in the students a lot more when they can see stuff fly. So I've built this capability slowly over the years at Penn State with a very simple sort of fixed-based TV screen simulator, and now we have our motion-based flight simulator. So this particular facility we got funded on a ONR DERP grant, and very glad to have some connections at Bell who've donated us equipment over these years. They donated their Bell BA609 cab along with the control inceptors for it. And we have a 6-channel visual system, provides a very wide field of view, and including a very good nose down vertical view, which especially good for landing and shipboard operation. We now have a pretty nice warping system that's all auto calibrated and gives a nice seamless image. That was not the case on some of our older systems. We had to do a lot of manual tuning to blend the image. I use X-Plane as a visual database and image generation tool. We don't really use the modeling in X-Plane, which it may be fine, but it's a little bit of a black box. So we use it just pretty much as a graphics engine. It's nice because it's, I can get students to go in there and modify the database. So we've built some ADS 33 MTE courses and some custom design MTE courses. And then we use touchscreens and VAPS XT for our symbology. We're also working with a company called Insco and using, they have a pretty nice symbology program too called iData. And then I interact a lot with a company called Simulation Control Technologies up in upstate New York, and they've provided, well, we've purchased both a control loading system and the motion base from them, and we've had great success with their equipment. The motion base is fairly limited travel. As you can see, it's motion within a dome, so we have to do visual compensation to not double count the visual display changes in attitude. But that was a pretty cost-efficient system we did there. Next slide. And then finally, indoor flight lab. So it seems like every university has a motion capture lab now. We built one about, 5 years ago or so. So we have a Vicon motion capture lab. Here we were kind of testing the limits on how fast we could make the UAV go in our lab. So I'm actually flying that with a gaming joystick back there in the right-hand corner. I am not a good RC pilot, so I really was relying on the controller, which is essentially like a TRC, position hold controller, to do that because we were going so fast, got a little overshoot. But these systems are great for research and education in flight dynamics. Again, lets the students see what's going on and dealing with the hardware. So I'll talk more about a project where we've used that lab coming up. Next slide. All right, so I'm going to dive into the technical material and go ahead and go to the next slide. Simulation control of eVTOL aircraft. So really got into this area mainly working with continuum dynamics, with starting with Dan Wachspress and also Jeff Keller through STTR and SBIR programs. So we've developed a tool to simulate this class of aircraft, and we make use both of MySim code as well as the CHARM module software, which gives you much higher fidelity modeling of the wake and interaction effects. So we're looking at things like ride qualities and gust rejection. Also, project with Kim Brentner and Eric Greenwood here, as well as CDI, looking at coupling of the aeroacoustics with the flight sim. Next slide. So it's an overview of the DEPSim CHARM software. So the idea is to do a mid-fidelity type simulation tool, where I say high fidelity maybe as complete CFD solutions. And we couple what would be considered low fidelity from an aeromechanics standpoint, which is just our PSU DEPSim flight code with rigid blades and finite state inflow model, and just sort of table-based lookup tables for interactional effects between rotors. But that model gives us a good starting point. You can trim it easily. It's completely linearizable, so you can linearize it. You can implement a controller, and it's quite flexible and easy to do those kind of tasks. We have electric motor models we can implement in there. It's all completely in state space form. And then on the higher fidelity side, we have the CHARM rotor module, which has complete free wakes, vortex lattice type modeling of the rotor blades and any lifting surfaces, and it's all completely coupled. If you model enough wake, you get all the interactional effects between the two. And so what we do is couple the codes. We have PSU DEPSim on the left, which starts running, and then we fade in the CHARM rotor module. We feed the controls and aircraft state to it. It does a complete free wake type solution and then returns the rotor forces and moments back to PSU DEPSim. And then we're able to evaluate, how good our controller design is, for example, once we go to the higher fidelity model. Next slide. So just some sample aircraft that we've done here on the right. We have a kind of generic eVTOL configuration, with quad rotor lift and then a pusher prop and a wing tail. We size it at about 1,000 pounds, so this would be like small single person type vehicle. And then similar type configuration, the NASA Lift Plus Cruise, larger, 6,000 pounds or maybe more. We've also done fixed wing like the X-57 configuration. Those are all OpenVSP type models. You could actually crank out your charm input data directly from those. We have the two codes, like I said, working simultaneously. So we have our baseline model or our uncoupled model that's fairly simple, but it's completely state space oriented, runs real time, linearizes itself. And then we have our coupled model where you can do flexible blades in charm rotor module and full free wake for all your interactional effects. Generally speaking, does not run in real time, especially when you have small high RPM rotors like these configurations. Next slide. So controller, we use a dynamic inversion controller. I say nonlinear dynamic inversion, although it's really uses like linear stability derivative models that are airspeed scheduled, and then you have the option of doing nonlinear kinematics if you want to do that. But essentially, dynamic inversion does an inverse of the plant and converts it to a simple set of integrators, and then you just design a classical controller around that. Talk more about that in a second. You have command filters or command models that govern response to pilot input. We have a separate controller for the longitudinal axis prop. And then a big part of this is control mixing. So there's control mixing within DI, but there's also at the outer side a control mixer, which maps your commands from the autopilot out to all the different types of control surfaces that you might have. So from these aircraft, you might have regular actuators that drive a surface or maybe collective or cyclic pitch on rotors if that's available. And then you have electric motors that you can think of as actuators as well. And the electric motors just drive variable RPM. And you may use a combination of the two. So we try to be very flexible in terms of setting an architecture where you can set the mixing however you want. You can even do some blending between, say, variable RPM, variable collected control. Next slide. So within DI, once you do an inverse the plant, what they call feedback linearization, like I said, it transforms the aircraft dynamics to look like, from a dynamic perspective, simple integrators, at least approximately within the approximation of your linearized model of the aircraft. Then once you have that, if all works out, you could just design a constant gain PID controller that governs what we call the error compensation. And go ahead and hit next. So that PID error compensation is then tuned to get the disturbance, rejection, and stability margins that you need in your design. And so, in theory, if you have an exact model of your aircraft, it's going to be guaranteed stable. But of course, in reality, there's unmodeled dynamics in the model you use for controller design. So we know that's going to be imperfect. So there really is still a tuning process we need to check to make sure you have good margins as well as decent performance in terms of disturbance rejection. Next. And then the inverse model could be as simple as just airspeed scheduled linear matrices, right? So you have your system matrix and a control matrix, as well as an output matrix, which converts states to controlled variables for each of the control axes of your controller. Next slide. We'll show a sample application of this. So we looked at this generic eVTOL configuration and focused really on the variable RPM case, because that is by far the most challenging to get a high performing and stable controller in these configurations. I think a lot of people are seeing that. And it's because of the added dynamics of your electric motor. And so with our basic what we call uncoupled model, just PSU DEPSim, we can linearize that complete high order model and get very good estimates of stability margins. But it has sort of low fidelity aeromechanics in terms of the rotor inflow and the interaction effects. Then for our couple model with the charm free wake, we can't really just push a button and linearize it, but what we could do is run simulations and conduct frequency sweeps. And so I think if you hit next, we could apply a disturbance there at a summer right before the mixing. And then next, we get an output just after that summer, and then hit next again. We get another output just before the summer. And with those two, that first output after the summer, we call our input, and the one before the summer is our output. And if you get that frequency response, that looks like your broken loop frequency response from a mathematical perspective. And so from that, we can analyze stability margins. Next. And then from the other perspective, we want to look at sensitivity functions. So this is a response of the closed loop system due to a disturbance on the system output. So if we inject next a disturbance here at a sensor output of one of our controlled variables, next, and then take, go back one, and then take the output just after that summer, we get a frequency response that's going to be equivalent to what they call a sensitivity function, a output due to an output disturbance. And from that, we can get disturbance rejection bandwidth, which is a good performance measure of how well our controller is working. Next slide. So we did this with our baseline model, variable RPM. And what you're looking at on the left there is a broken loop frequency response, magnitude, and phase. And then we did the same thing with our couple model with the charm rotor module. And we have a gain parameter we call natural frequency, omega n, that we can increase to go simulate higher gains in the controller. And as you do that, next, we see an increase in the magnitude of the loop transfer function, and therefore an increase in the gain crossover frequency. And then the side effect of that is that tends to reduce your phase margin as you increase your gain crossover frequency. So what it means is you increase the performance of your controller, but you get less relative stability. Next. And then on the other side, we look at the disturbance rejection bandwidth frequency response. So this is the sensitivity function. And when you look at the magnitude there of DRB pitch axis, you see very low magnitude at low frequency. That's where the controller is rejecting disturbances. And then eventually you get a crossover, and where it crosses -3 dB is called the disturbance rejection bandwidth. And again, next, as we see increased gain, we move that disturbance rejection bandwidth frequency out to the right. And we're doing analysis here, those left-hand figures with our simple uncoupled model, and then on the right-hand figures with our fully coupled model with the charm rotor. You'll notice on the fully coupled model, we have a coherence plot because those all have to be done via system ID, which we use the Cipher software to do that. Next slide. So the net result is that you get similar trends, but different net performance trade-off in terms of higher performing controllers and relative stability. So next, that trend is increasing gain. You get better disturbance rejection bandwidth. So you're rejecting more disturbances out to a higher frequency, but your phase margin gets lower. And the green line shows with our simple model, we could push the gain out pretty high and stay above 45-degree phase margin, which is your normal design requirement. But when we add this complex free wake, the picture is not quite as rosy. So you see a much larger degradation in phase margin as we increase gain. So it's an important takeaway in terms of studying the design space really for the performance of your controller. Next slide. So this just sums up what I said. What we think happens is the free wake adds some kind of phase delay in the response that degrades our stability margin, but it's something we're still looking into. Next slide. A couple other things we're using this software tool for, and I had to show some good wake visualization from Charm. We're working some with U.S. Army, Mark Scott and Jeff Sensei on analysis of UAM or advanced air mobility configurations. So we have a model that's sort of notionally like the beta configuration, and then another project been involved in is the Dragonfly, which is a pretty cool project. So that's where the plan is to send a drone to Titan, which is a moon of Saturn that has actually a very dense atmosphere, even denser than Earth's. So they want to make the lander essentially an octocopter that will fly on a planet with very dense atmosphere and much lower gravity, which you would think would make things much easier, but it adds some interesting complications as well. And where we're really using DEPSim Charm is looking at aerodynamic interaction effects, specifically things like wake impingement on the tail and rotor-to-rotor interactions on these types of configurations. Okay, next slide. All right, so the next topic I'm going to talk about is external slung loads. Next slide. So I've done a few different projects. The slung loads are great topic to study from an academic perspective. You get coupled dynamics between the helicopter and an internal slung load. So you have something that looks like a pendulum that's also driven by aerodynamic forces, and that it's been interacting with the helicopter dynamics as well. The first thing we looked at was low speed slung load stabilization. Most people think of high speed being sort of critical for external slung loads, but if a pilot has to place a load precisely on a spot, it actually is a big pain if the load's swinging around like a pendulum. We designed a lagged cable angle feedback controller that basically measured the cable angle and fed back into the aircraft flight control design. We demonstrated that with our GenHel model, the UH-60, and showed that we could use that controller to basically damp out the load motion almost instantaneously. And with a controller that was very robust, it actually intentionally adds lag in the feedback. So it means that your design tends to be very robust to any latencies in the system. And that was opposed to using a lead design with like essentially a derivative type controller that a lot of people were looking at. Multi-lift, this was really cool stuff. So you know, there's been this idea for years and years is that we don't really need to make a really large helicopter. We just need to get helicopters to work in teams to carry the really heavy loads together. It never came to fruition for the obvious sort of safety reasons associated with it. But now with better modeling, better flight control tools, it seems a lot more viable. So we did a lot of modeling and simulation of this, developed different types of control algorithms, and then really mainly Jack Langelon and his student Jenny Geng did some hardware implementation and flight testing of this. So you can see there on the middle right, the team of quad rotors carrying essentially like a beer cooler. There's no beer in it. There's only avionics, and in fact, the controller was set up that Jenny would fly that team based on where she wanted the external load to be, and then the processor on the external load coordinated control for the 4 UAVs. And then finally, the last 5 years, we've really been looking a lot at stabilization of slung loads and high-speed flight. And this was pretty cool too, because we had some wind tunnel testing involved, and got to work with Aviv Rosen at Technion, Israel, on this project. And for that, we've been looking at using active cargo hooks to stabilize loads at high speed. And this is the project I'm going to focus on. Next. So focusing on the high speed stabilization of external slung loads. Next. So external slung loads, every time you have a load, there's a handbook requirements that tell you, how fast you're allowed to carry that load on a particular helicopter. And in many cases, the speed limit is not related to loads or performance issues, but due to load stability issues. So some loads, for example, you can't carry faster than 60 knots. And you can imagine having to only go 60 knots in a helicopter that normally flies 120, 140. That's a serious reduction in efficiency. So people have looked at active control techniques. I talked about the low speed and hover stabilization. Similar controller that we developed was also tested by Boeing and the Army on an H6 flight test. The Army also tested cable angle feedback controllers on Rascal. On the H6 test, they actually used active cargo hook controller. And this is very appealing because you don't have the complexity of integrating with the aircraft flight control system, although it does require added hardware to the vehicle. Now, as we look at FVL, we're starting to look at helicopters going much faster, 200 knots, and the load stability issues are going to become even more of a challenge. So the question was, well, maybe an active cargo hook buys its way on one of these aircraft if it's going to let you carry these loads out into their high-speed flight regime. Next slide. So if you saw in the previous slide, that was the AVX FVL configuration with an M105, M119 howitzer, which is a 105 millimeter howitzer used by the Army. We chose this as our sort of target load for this study. We got a nice model built by one of these companies that build scale models. And then my colleagues at Technion, Ruben Raz and Aviv Rosen, actually embedded masses in the load to emulate the scale inertial properties. That howitzer, you can carry it, you can fold it up and carry it that way, or you can leave it in its 20-degree firing position and carry that way. So we actually looked at both those configurations. And the Technion, Aviv showed in the past that these slung loads fruit scale quite well. They've actually validated that. So you can do fruit scaling of the load at 20-to-1 scale, and then you can use a much lower tunnel speed to simulate the equivalent full-scale airspeed. So, whereas 200 knots comes down to about 23 meters per second tunnel speed. The frequencies scale down by square root of n, or scale up by square root of n. So you get higher frequencies on the model scale. So they set this up in tunnel. Ruben Raz developed a active cargo hook model, basically using parts from a 3D printer. Gives both longitudinal and lateral motion of the payload. Everything was instrumented very nicely. There's IMU on the howitzer model. There's also potentiometers measuring the cable angles and a load cell as well. Next slide. On our side, along with Kobe and Sue, who was worked for me as a research assistant professor for several years, and my graduate students, we did analysis of the tunnel data. And first question we had when we started this, well, will the load even go unstable as you go up to high speed? Well, sure enough, it definitely goes unstable. What you see are what are called limit cycle oscillations. So this is a kind of periodic equilibrium that you see in nonlinear dynamic systems. What happens is it always tends to an oscillation of the same amplitude and frequency, or it can even be more of a complex orbit, not just a pure sinusoidal oscillation. And so we see at 101 knot equivalent full scale, we're starting to get about plus or minus 2 degrees oscillations in pitch and roll, which may be okay, but you're going to start to feel that in the aircraft. And then as you go up to 154 knots, they tend to become a little more violent, more like 5 degrees. And then eventually it goes out of LCO into what would only be called chaotic type motion, where there's no significant pattern, but the oscillations become very large and actually would be quite dangerous. You can see they're twisting almost 180 degrees and pitch near 90 degrees. Next slide. So there was definitely a problem to address. So we hunted around for a good way to design a controller, and ultimately the method that works, kind of surprising, is even though we're seeing these LCOs and chaos, which are all nonlinear system phenomena, we designed a linear controller and found that we could be successful. So we couldn't get a linear model above 100 knots full scale because the system was always in LCO or worse. So we linearized around lower speeds below 100 knots full scale, where the load would actually show a stable equilibrium. And so we conducted frequency sweeps with the active cargo hook, and with the help from the Army, we got simple linear models of the cable angle response to the cargo hook displacement. And so what you see here on the right is a fit of identified transfer function, I should say, of cargo cable hook angle to the displacement input, and it's modeled by second order linear transfer function with the time delay. And then we designed the controller based on this linear model, and then said, well, then let's see how it works as we go out to higher speeds. Next slide. So the controller we designed, we looked again just at, we actually looked at numerous methods, modern methods, but the one that really did work well was classical control design. And we looked at a lead design method, which is essentially a derivative and a low pass filter to filter out noise, and then a lag design, which was a washout filter coupled with a low pass filter tuned to get the right dynamic compensation. And we looked at both configurations. Interesting, if you do the lead design, your gain is of opposite sign as compared to the lag design, because if you look at, from a Bodie perspective, we're looking at different places on the frequency curve where the phase is shifted almost 180 degrees. So you use a positive gain on one and a negative gain on the other, and they both stabilize the system. And we did it both for, simple decoupled controllers, both for the lateral axis and the longitudinal axis. Turned out the design was pretty robust, whether you're using the firing configuration or the folding configuration, and it stayed pretty constant throughout airspeeds as well. Next slide. You can look at these designs from a root locus and stability margin perspective. So on the left, we have the lead design, and on the right, we have the lag design. And both of them basically take your pendulum modes, which are the axis on the imaginary axis, and drive them over to the left a little bit. But with the lag design, we could get it much more stable. Not only that, there was no unstable branch going to the right. And when we looked at phase margin, we got much larger phase margins with the lag design, and even more importantly, much larger time delay margins. So we could accommodate up to almost 175 milliseconds of time delay for our lag design, where the lead design was only robust up to about 50 milliseconds. And it would have been quite possible we would have had 50 milliseconds just in the sampling delays we had in our implementation. So we chose the lag design as the more robust and really better performing solution. Next slide. So this is a video. I think you should be able to start it, Chris. So this is the howitzer in its firing condition in the wind tunnel. You can see it actually yaws almost like 30 degrees in equilibrium. And they're ramping up tunnel speed, and you can see it goes into an LCO, and it's actually going up past 160 knots full scale. And then we engage the controller, and the oscillation just dampens out. And it's continued to run after that, and with no motion whatsoever. I think the video stopped now, but so it was pretty powerful method. We went from what was otherwise a very violent oscillation at the plus 160 knots airspeed regime to a stable system. Next slide. Okay, so moving on, I'm going to talk about shipboard landing. Next slide. So again, a topic I've worked on in a variety of projects. Early years, a lot of people were looking, have been looking at ship air wake effects. So the flow over the ship creates separated, unsteady flow that interacts with the helicopter and becomes an issue in terms of pilot workload, and can even limit the certification of the landing spot for certain wind conditions. Does some recent work with Sven Schmitz here on coupling atmospheric boundary layer effects, CFD of the ship, and the aircraft flight dynamics. We even looked at fully coupled CFD with flight sim. That's what's shown in that top picture there with my student Ilker Ulrich. And a lot of work on controller design, advanced control modes, so things like ship relative TRC and position hold, as well as autonomous modes. And then scaled experiments of autonomous ship landing. This is something we've been working on just the last couple years. We're taking some of the lessons we learned in control design for ship landing and actually bringing it into the model scale and doing very realistic testing on ship models down at the MASC facility at Carter Rock. Next. Oh, that's just the animation of one of our simulations of a H-6D landing on a back of a destroyer with our autonomous control modes. So controller actually uses deck motion prediction. So it predicts where the deck's going to be ahead of time and then plans a trajectory accordingly. So. Next slide. Okay, so scaled experiments on autonomous landing in high sea state. So these results are actually very new. They haven't been published just yet. They've been submitted for publication for the AIAA meeting coming up in June next year. So the idea of the task is to develop a scaled experiment to look at ship landing, to sort of better understanding what the requirements are to obtain fully automated ship landing in high sea states. The MASC facility is in Carter Rock, amazing facility. It's basically a giant wave tank. The Navy conducts tests of different ship models in the facility. And Carter Rock has actually installed a OptiTrack motion capture system. It's like a Vicon system. It's a different brand. And so we actually got permission to fly drones in the facility. And we can use this OptiTrack system for control as like a surrogate GPS. The MASC can create all variety of sea states, different wave heights up to what would be equivalent of 5-meter waves in the ocean, or even larger, probably different angles and different unsteady type wave conditions. We've been doing landings with the OptiTrack system, but we've also with Jack and his student implemented vision-based systems from an onboard camera. So we actually have a camera system on board the drones that can look down on the ship. We put a special marker on there called a recursive April tag that aids the vision algorithms in terms of estimating the state of the ship deck. And if we compare our models and the ship model that we used in the test, the scaling is similar to like a V-22 and a DDG destroyer at 1/25th scale. So if we look at our multi-rotor drones up here and look at the distance between two rotors, compare that to the length of the ship, it's similar as 1/25 in terms of the V-22 rotor distances and the length of the DDG. We have two test aircraft, a hexcopter and a quad rotor. They both feature very watertight boxes for the electronics, and we've already tested those the hard way. So we already had one aircraft that got the kill switch inadvertently through a software bug and landed in the water. And amazingly, no damage to the aircraft at all. The watertight box kept out all the water, and even though it fell from about a good 10 feet, there was no damage to the aircraft. And inside that box we keep a PX4 type autopilot system, that includes IMU, magnetometer, which is actually a very limited use in that facility. It has wired, Wi-Fi receivers where we can transmit the OptiTrack data over to those aircraft, and they effectively use that as like a GPS. Next slide. So here's a test setup. So we have our motion capture system, and we tested this, of course, initially in our own motion capture lab. So that can either be the OptiTrack or our Vicon system that we have at Penn State. It captures both the aircraft dynamics as well as the motion of the deck, if you want to use that. We have our onboard camera. That data goes through a unscented Kalman filter to give a relative deck state estimation. We could use either of those state information, and we've actually done autonomous landings using both. And then we have our controller on our secondary processor, which is essentially like an Android processor that does trajectory generation and outer loop control. And then we have the Pixhawk PX4 processor on board the aircraft that does our inner loop control. Next slide. So my student, Chris Hendricks, done a lot of the work on the controller design. What he did was he implemented an explicit model following controller within the PX4 architecture. And what he did is added essentially he redesigned the attitude loop while keeping the PX4's internally designed rate controller. And we did frequency sweep testing in our own motion capture laboratory and processed the data with Cypher and able to get fairly accurate models of the quadrotor and hexcopter dynamics with their rate loop closed. So we kind of have a plant model which includes some feedback augmentation already in it. And then we can design our attitude controller around that in such a way that we have very good control in terms of tuning the bandwidth of our flight controller. And so the idea is in the long term is to have really scalable control laws where we could tune the bandwidth and simulate full scale aircraft through the fluid scaling. Then there's a trajectory following controller outside of that, which uses sort of a simple DI concept. And then we have trajectory generation. We've been using TAU guidance, which also incorporates a very short-term ship motion prediction. We look at our controller, the first controller we designed, it has a bandwidth of 13 radians per second, which is very large, but typical for a small scale UAV. And you scale it down to something like a V-22, it's 2.7 radians per second. So, maybe about right for an aircraft that size. And the plots there just show our verification of our identified frequency domain model and then the time domain verification as well. And we have very good match with the flight data. Next. So here are some sample results. So we did 25 successful landings. We didn't have actually any unsuccessful landings, which was amazing. I think it's because it happened the day after I left and Jack was there and I wasn't, so I didn't get to see any of the successful landings. But we did it both using the OptiTrack and using vision-based landings using a real-time onboard unscented Kalman filter, which I thought was quite impressive. Student Duncan implemented that algorithm. We went up to 0.2 meter waves in the mast facility, which scales up to 5 meters at our full scale. So those are big waves for a ship model that size. And the plots here just show a sample simulation. You can see, they can control the blades very well. So that yellow is the ship deck motion as measured by OptiTrack. It looks like a nice perfect sinusoid. Then the red shows the actual aircraft response, XYZ and yaw, and then the blue is the commanded. So we're tracking our command well when we come down and it's set down fairly softly on the deck. There's a lot of future work in terms of trajectory generation. One of the big things we want to look at is integrity checks to support a robust system where you would know when to abort a landing based on new information on the ship motion. And then we also want to look at what are the controller bandwidth requirements to do these types of test successfully. Next slide. All right, final projects, control design for high-speed rotorcraft. Next slide. So number of different projects in this area looking at the compound rotorcraft. So interesting thing about some of these future configurations is they have a huge amount of redundancy and control effectors. So you have a lot to play with in terms of enhancing performance, handling qualities, survivability, and cost of operation. So I was lucky to have Tom Berger come and do his PhD with me a couple years ago, and he did his thesis on handling requirements and control design for high-speed rotorcraft. He looked at both a tilt rotor and a coax, the generic configuration. Looked at the control allocation. So these little spider plots up here show how you allocate control between different rotor control surfaces and aircraft fixed, type surfaces to achieve your desired roll, pitch, and yaw moment, and it changes with airspeed. And then he did complete handling quality studies with several different pilots. He did this both at the VMS out at NASA as well as in our sim, and showed what the benefits were for adding outer loops on some of these controllers, a couple of different configurations within those as well. Load alleviating control, student Umberto, who's actually down there in Alabama now at Auburn, did some very nice work looking at high order linear models derived using harmonic decomposition so that we can incorporate rotating system type loads in our control synthesis. And then next, I'm going to focus now on Piasecki aircraft, the U.S. Army's ADAPT program. And I actually have, Chris is also involved in the program a little bit. So it's of interest to him as well. Next slide. So the slides I could get released from this were already published at the VFS Vehicle Management Systems Conference in August. So sorry if it's a repeat some of that. But the idea of ADAPT is to develop and demonstrate improvements to safety, survivability, and performance by taking advantage of advanced flight control and the use of redundant control effectors on these high-speed rotorcraft configurations. So it's a pretty ambitious, broad program. It involves control system and software architecture design, simulation, which is the main part I've worked on, but they're also doing subscale testing, and they're even bringing in some aircraft to do full-scale testing, so aircraft big enough to hold a pilot. Next slide. So this is the sort of general control architecture as we applied it specifically to called the X-49 aircraft. And X-49, talk about in a minute, is a compound helicopter demonstrator derived from the UH-60 that the Piasecki developed and flight tested about 10 years ago or so. The idea of ADAPT is to have a control architecture that you can lay on top of existing control laws to add additional functionality. And includes something called FTO, which is a trim optimization controller that works in the outer loop. VMO, which is also like a trim optimization controller that works at faster timescales to enhance performance and maneuvering. And then for the safety survivability side, damage tolerant control. And that's in the form of a adjustment to the control mixing matrices to recover from failed control servos, as well as neural adaptive control to enhance the control performance in those cases, and command model adaptation to constrain the maneuvering envelope once you get into these failed cases. Next slide. So flight optimal uses trim optimization. So the idea is you fly the aircraft, you measure some performance objectives like fuel flow or even vibration, and it adjusts all your control surfaces to get the optimal trim. So unlike a conventional helicopter, these aircraft, you could achieve different balance in terms of lift on a wing or a main rotor, and different propulsive force balance between a propeller and the main rotor, as well as force and moment balance from different control effectors. And so how do you take advantage of that to get the best performance? VMO is an extension of that to use that in maneuvers like climbs and turns and pull-ups. And then DTC is reconfiguration of control laws, again, taking advantage of your redundancy. We've also, on the software side, we have an executive and different types of interface managers to bring all this stuff together. Next slide. So the first aircraft we implemented this on was the X-49 because we had flight data, a good model of the aircraft. We call the aircraft X-49S because the original X-49A had mechanical flight controls and the partial authority SAS. We added, really to achieve this technology, you need something like full authority fly-by-wire. We also added larger elevators to get more control redundancy and pitch, and we added the capability to vary RPM up to 10%. So the aircraft has, wing flaperons that are actuated. It has elevators. You can vary the rotor RPM plus the main rotor controls, and then a variable pitch prop that you can use to change thrust. So there's all this different control redundancy to take advantage of. Next slide. So I won't be able to get into the details of all that implementation, but what we did was pretty cool in a test I guess earlier this year. We did a full mission scenario of the aircraft. So if you hit next, we started the mission with a notional troop insertion. So we had, we weighted the aircraft to have 12 troops on board. Next, the aircraft flew out in a pattern, and we tried to sort of minimize fuel flow with flight optimal during that segment. Next. And then we did a terrain course, low speed terrain flight, low altitude, high speed terrain flight through an area and went to an LZ and landed the aircraft, removed the troops from the weight of the sim model. And then next, went on to the next segment. Can you hit next? The next segment was a new phase. The idea is now there's a message that there's a downed air crew and need the aircraft to recover them. So we do another segment where we do fly at VH, and we use FTO mode that maximizes your speed, relatively long segment over 20 miles. I should mention, if you look in the upper left-hand corner, we did this in our flight sim here at Penn State, and we used sort of these large hoops to provide waypoint navigation for the pilots to do the mission. Next. And then there's a loiter where the aircraft needs to loiter, minimize fuel flow at your VBE until they locate the aircrew. Next. And then another another low altitude terrain course. Now, these terrain courses take advantage of the vehicle maneuvering optimization aspect of the controller. So you're maneuvering at pretty high G in some of those segments. So they fly in there, they land, they pick up the pilots. Next. And then the next segment takes advantage of a vibration reduction mode, an FTO. The idea, we want the passenger comfort on that segment. Next. But then there's threats again. So there's a terrain course. Next. And finally, the aircraft's low on fuel and needs to get back. So we go to a best range mode with FTO. Next. And then finally, next, we get a enemy fire that damages the aircraft, causing significant control damage. And we simulated, I believe, both damage to the tail as well as damage to one of the main rotor servos. Next. And so at that point, DTC has to recover the aircraft, and then the pilot has to return at the closest airfield. Next. So this shows results. We did the simulations several times with a few different pilots, both with ADAPT on and just with the baseline flight controller, and analyzed all the segments in detail. And you can see we use all the different control modes of ADAPT throughout the test. Without ADAPT, the aircraft was not recoverable on the damage scenario, so that the flight ended exactly at that spot. The vehicle couldn't be controlled, whereas with ADAPT, they were able to get back to the emergency landing field and do a roll-on landing each time. Next slide. So summary, I'll be quick. Significant reductions in fuel consumption at the various segments due to the different FTO modes. Hub moment reduction, which reduces vibration on the aircraft, was very large. That's pretty straightforward optimization where you trade hub moment with the elevator on the aircraft, and we had higher speeds through VMO and FTO5 segment, not huge improvements, but significantly faster on VMO, and actually burned less fuel on the VMO segments as well. And maybe most importantly, with ADAPT, the aircraft was recoverable. One of the pilots of the program developed a survivability rating scale, and they were able to get 3 on all those cases, which means the aircraft's be able to land, although slightly outside of envelope, whereas 5, it was unrecoverable without the ADAPT damage tolerant control. Next slide. So we continue to work the project. A lot of work on architecture to make it agnostic. So right now in simulation, we're actually have implemented the algorithms on the generic coaxial compound configuration, and we're setting it up so that the software is actually the same in both cases. You just have a different configuration set up for each. I mentioned the scale model tests, and we're actually going to be implementing on a tilt rotor configuration as well, and be testing that in the NASA VMS. Next slide. So finally, just credits. I'm sure I forgot some people here, but these are the sort of main PIs on the different projects. I know I forgot Anish Sidney from Carter Rock. She should be on there for the shipboard stuff. But all these were very collaborative projects with a lot of different people. So I want to assign credit and thank all of you, and I'd be